Okay, so we're going to now answer the question that if the Earth orbits the Sun in a circle and there's a centripetal force acting on the Earth toward the center of the Sun, or at least toward the Sun, what is actually supplying that force, right? What is responsible for supplying that force? There's obviously not an actual rope that is connected between the Earth and the Sun that's supplying any sort of tension, so what in fact is it? And you may have been able to guess, but the answer is in fact gravity. And this is a very important point to note, that gravity is indeed a force, even though it doesn't exert a physical push or pull, or I should say that it's not physically connected. So the gravity is a type of force that we call a field force. Okay, so it's not physically touching the Earth, or there's not a physical rod connecting the Earth and the Sun. But it is exerting a force nonetheless, and so that type of force is called a field force. Whereas the tennis ball and the string is in fact attached to the tennis ball, so we call that a contact force. Okay, so what we want to talk about now, bringing up the Earth and the Sun, is we want to talk about the solar system. And we'll talk just a little bit about early views of the solar system, the Copernican revolution, and then ultimately Kepler's laws, culminating with Newton. Okay, so originally, the original model of the solar system, this was built by the Greeks. Not ancient Greece, but ancient Greece. Okay, so in ancient Greece, the idea was that the Earth was the center, and everything revolved around the Earth in concentric circles. And that's because the circle was perfect. A true circle has no blemishes. And so for ancient Greece, for ancient Greek thinkers, true beauty was paramount. And so because the universe was beautiful, therefore the true nature of the motion of everything in the sky must be a circle, because it had to be perfect. And this was culminated the entire structure of the solar system was finally tuned, if you will, by this man named Ptolemy, and everything in the night sky worked like clockwork except 5 things. There were 5 rogue bodies that didn't behave like the other things in the night sky. And because these things didn't behave normally, they were named planets, or wanderer. Okay, they were named wanderers. That's where the term planet comes from. And so, what initially they tried to do was then determine if there was any pattern to how these 5 bodies moved, and in fact there was. And by the time Ptolemy came around in about the 3rd or 4th century AD, they had a quite sophisticated system to determine the paths of these bodies. And the bodies that were visible at the time were Mercury, Venus, Mars, Jupiter, and Saturn. Okay, these were the 5 planets that were visible, or that are visible to the naked eye. All right, and they just didn't behave like everything else. And Ptolemy built this very nice model. He improved on it, but the basic model says this, that here's the Earth, and then here would be the Moon, and then here would be Venus, and then here would be Mercury, and then here would be the Sun, and then you'd have the 2 outer planets, and then the rest of the sky was beyond that, and everything revolved around the Earth in perfect circles. The problem is that these rogue planets didn't behave in just this nice manner. Sometimes they would move backwards, right? Sometimes they would move backwards. And this is what we term retrograde motion. Okay, so Ptolemy, to counteract this retrograde motion, came up with the idea of deference and epicycles. And the idea is that if this is the Earth, then, say, Venus orbits around the Earth, and this main circle that it follows is called the deferent. But on that deferent could be a smaller circle that Venus orbits on, and this is called an epicycle. So the idea is that as the epicycle orbits along the deferent, then Venus orbits along the epicycle. So the overall motion that you get from this pattern is something that looks like this. Right, that's the overall pattern that you get. And so it's these points right here where along the epicycle the planet seems to be moving backwards. So when Venus is right here, it's moving in the same direction as the epicycle is moving, but when it's right here, the epicycle is moving this way, and the planet would be moving that way. So they'd be moving opposite to each other. So that explained the backward motion. And that was accepted for thousands of years, until Copernicus came along. And Copernicus built a heliocentric system. The Ptolemaic system is called geocentric, geo meaning earth-centered, whereas helio means sun-centered. Okay, so this is a sun-centered system. And Copernicus initially put all of the planets in perfect circles around the sun. So if this is the sun, then Mercury, Venus, and Earth. Imagine these are all perfect circles. Okay, so in the original Copernican system, the Earth, Venus, and Mercury, and Mars and Jupiter and Saturn, for that matter, all orbited the Sun in perfect circles. Now, initially, this model did not do any better at predicting the places of the planets than the Ptolemaic system. So it originally did no better at predicting planetary positions than Ptolemy. Okay, it originally did no better. And I should specify this. The Ptolemaic system, okay, when the epicycles, when the original idea of the epicycle did not improve, or I should say did not significantly improve the ability to predict the positions of the planets in the sky, what they did was they then added another epicycle on top of the epicycle. And then they would place the planet on that. And then when that it got better, but still not perfect, they would add another epicycle, and then another epicycle, and another epicycle. And by the time Copernicus came around, there were about 10 epicycles per planet. So each planet had about 10 of these things that Ptolemy had put on there to try and describe these things. So the whole idea for Copernicus was to simplify the math. Okay, that was what his motivation was, and the math did turn out to be more beautiful and more simple, which are actually the same thing in physics. If you put things at the if you centered things on the sun. Okay, so but again, his system did no better at predicting planetary positions, and so for a short time it really did not gain much attention. However, along comes a man by the name of Johann Kepler, who was able to determine precisely the orbit of Mars. And how did he do it? So for years and years he struggled with this process, and it took him about 8 years to finally do it, but along the way he had an epiphany. And that first epiphany was, do away with perfect circles. Once he was able to ditch the idea of the circle, which may seem like a common sense thing to do nowadays, if something doesn't work, try and think out of the box. But remember, the idea of the perfect circle had been so ingrained into astronomy by that point that this was a really large break with convention. This was very provocative, if you will. So, in doing so, he determined that planets orbit in circles, but ellipses. Okay? So what is an ellipse? It's more or less an oval shape, but it has a very distinct property. Well, it has a few distinct properties, but the basic of which is that there are 2 points within the ellipse. These are called the foci, and each one is called a focus. So there are 2 foci within an ellipse. And there's a property that says anywhere on the ellipse, so if my planet is right here, if I measure the distance from both foci, we'll call it R1 and R2, the sum of R1 plus R2 will always be constant. So anywhere on the ellipse, I can be right here, and this can be R1 and that can be R2, or I can be here and that'll be R1 and that'll be R2. It does not matter where I am. If I add up both R1 and R2, they'll be constant. Okay, so that's the idea of an ellipse. And this led Kepler to redefine planetary motions. And once he was able to fit these orbits for these 5 planets with ellipses, the predictions were darn near perfect. Okay, so he was able to greatly improve the precision with which planetary motions would be predicted. And this led to his first 3 laws. So Kepler's laws, in order, are 1, all planets, all planets orbit in ellipses with the sun at one focus. Okay, so if we go back to this diagram, one of these will be the sun. Okay, one of these will be the sun. And number 2, planets sweep out. Planets sweep out equal areas in equal times. So what this means, okay, what this means, let's draw a fresh ellipse here. What this means is if I have 2 foci, and here's the sun. This was another major break with convention, because if everything moved on perfect circles, then everything had the same speed. Kepler's second law indicates that planets and other solar system bodies like comets and things, comets particularly, don't move at the same speed. The closer they are to the sun, they're going to move faster because they're feeling more acceleration than if they're out here. And the other focus is just kind of right here. So if this is a comet, on an orbit, it's going to move fast toward the sun, and it's going to move slow away from the sun. So what Kepler's second law says, let's go back to it, planets sweep out equal areas in equal times. What this means is, if I look at any 2 given time intervals, so let's say that I look at the comet when it's right here, and I start my stopwatch, and maybe 2 months or so, maybe after 2 months it's moved to right here. If I then, I'm going to redraw the sun up here, okay, if I look at the area that's been swept out in this region in here, okay, this is approximately a triangle, and for very short time intervals this will be almost exactly a triangle, but you have to take the curvature here into account a little bit. But this enclosed shape, right, kind of like an ice cream cone maybe, is going to have some area to it. And Kepler's second law says that if I have if I sweep out this much area in some time, let's say this was 2 months, and then I wait for the comet to go to the other side of its orbit, and then start my stopwatch and go another 2 months, it might have only moved to about right here. Okay, So then if I draw a line connecting these two and the area inside here, notice this is much more shallow. Kepler's second law says that the second area and the first area are equal. Okay, that's what Kepler's second law says. Because the planet's moving faster, closer to the sun, it's going to sweep out a larger angle. But because it sweeps out a larger angle, it's closer to the sun. Therefore, these sides right here aren't going to be as long. Whereas away from the sun, it's not going to sweep out as large an angle, but these sides are incredibly long. And so if you add up all of the blue stuff in here, those areas are actually going to be equal. Kepler's third law is known as the harmonic law. And this says that the square of the orbital period or the time to complete one orbit is proportional to the cube of the semi-major axis. Okay, so there's a lot in here, but this will actually turn out to be one of the simplest and the most useful of the three laws. So the orbital period is, again, just the time it takes to complete one orbit. So Earth's period is 1 year. That's how long it takes the Earth to go one full revolution around the sun. So what is this semi-major axis here? Okay, so let's draw one more ellipse here. And what I can do, if this is a focus and this is a focus and this is the center, then this ellipse has some properties. And that is that the distance from one end of the ellipse to the other end along the long axis is called the major axis. And then the distance perpendicular to that along the smallest axis is called the minor axis. So the semi-major axis is just half of the major axis. So the semi-major axis goes from the center to the end. Okay, so the semi-major axis is just from here to here, right? That's the semi-major axis. Another way to think of the semi-major axis is the average distance from a planet to the sun. Okay, and for a planet like Earth, okay, a planet like Earth, if this is the sun, our orbit is almost a perfect circle. It's not quite, but it's very, very close. So our semi-major axis, if this is the Earth, is literally just the average distance that we spend away from the sun. And it's going to be very close to constant. In fact, our orbit is so circular that even though the center of the sun is at one focus, the other focus is still within the sun's interior. Okay, so our orbit is darn near circular. But what mathematically this means, okay, what mathematically this means is that the square of the orbital period is proportional to the cube of the semi-major axis, and we denote the semi-major axis by lowercase a. Okay, so what this means is that the square of the orbital period is proportional to the cube of the semi-major axis. And if you use, pardon me, a certain set of units, in fact, you can actually write this as an equality, at least for planets. Okay. Now it turns out that this is actually true for other two-body systems, things like binary stars or other types of systems, a star and a black hole or whatever. So this is a very general law, but in fact, if you use a specific set of units, you can actually write this equation as is, and it is perfectly valid. Now, Kepler was about 100 years before Newton. Well, at least he was doing his work about 100 years before Newton. And this law, okay, this law is actually what prompted Newton to try and build a model of gravity that would explain it. Okay, so it was actually this law that prompted Newton to try and build a theory of gravity. It's probably true that Newton was sitting in an orchard and probably saw an apple fall, and that's what got him started down the road. But it was his desire to actually show theoretically why this empirical equation was true that prompted him down the road toward his theory of gravity. And we'll talk about that theory of gravity in the next video.